ahead, Davit.
Thank you. My name is Davit, and I will be giving a presentation on my thesis titled Integrated Performance-Based Seismic Design, Traversing Affordances for Practical Implementation. It's not working. Following several economically impactful earthquakes, building performance definition needed immediate refinement. While traditionally seismic guidelines have performance objectives to protect human lives and prevent collapse of buildings, with the introduction of performance-based earthquake engineering, an approach was developed to quantify the performance of a given structural system in a probabilistic framework and express it in terms of metrics meaningful to stakeholders and building owners. Below is the famous PBE chart, the details of which I will not get into, as it is quite famous and probably all of you are aware of. As a consequence of this methodology, several documents were developed, one of them being the FIMA P58, where it allowed the performance to be quantified in terms of metrics like expected annual loss and mean annual frequency of collapse. However, due to their probabilistic nature and computationally expensive implementation, those have been popular primarily within academic research or specialized reports, while rather than widespread code-based implementation. Therefore, as you can see, there is an immediate need in developing PPE-compliant design methods for which this thesis will be focusing on. The goals of the thesis are to demonstrate the applicability and implement risk-targeted, loss-driven design methods in line with PBE objectives. In particular, a framework is developed within the thesis to obtain seismic design by limiting economic losses and targeting collapse safety. A methodology is proposed that is affordable for both practitioners and can be implemented for academics as well. Additionally, Python-based modular applications were created together with a story loss function generation framework and codified, leading towards traditional design and detailing of structural elements. In line with the main objectives outlined, the thesis is structured in several chapters. Here we will first have a look at existing seismic design code and recent developments in risk targeting seismic design approaches. Next, we will discuss some of the approaches to deal with loss assessment, that is the component-based and story function-based approaches. And we will propose the developed integrated performance-based seismic design framework. To aid that, the story loss function generation methodology was also developed and implemented. Finally, the framework was applied and validated towards risk-targeted and loss-driven design. Let's first have a look at some of the design code approaches. Traditional methods primarily focus on ensuring life safety of buildings by preventing collapse. Additionally, performance at frequent levels of shaking is checked and verified. Those are some of the design code approaches, and most of the design methods utilize what is termed as force-based design, or FBD. It is based on a calculation of a design-based shear force. Despite the codes having an option to use nonlinear time history analysis, it is considered as computationally too expensive at times, and therefore, given the availability of simpler linear methods, those are avoided. While FBD boasts a simple, an attractive simplicity, several shortcomings have been pointed out. Displacement-based design was advocated where deformation demands drive the design process. One of the main arguments was that it is not reasonable to quantify expected ductility and spectral demand reduction factors through unique behavior factors. A proposal was made to use a ductility and typology-dependent spectral reduction approach. Both force-based design and displacement design solutions are good approximations for initial seismic design of structures. Oh, what happened? Initial seismic design of structures. However, neither explicitly neither explicitly are risk consistent without any further modifications towards them. And parameters like performance parameters like economic loss, downtime, or collapse risk do not explicitly feature in the design process. Having seen the traditional methods, Let us discuss some of the recent developments in risk-targeted approaches. Any risk-targeted approach aims to control risk of exceeding a limit state related to a performance of a building. Here we provide a critical discussion of some of the available methods in the literature, as well as the proposed framework termed as IPBSD. However, this is not exhaustive, obviously, and more capacity design methods are available to the reader. Inspired from the performance-based seismic design notions, seismic classification of structures was formally introduced and implemented, which is a very important leap towards codification of such approaches. Let's now have a detailed look at some of the existing approaches and how they fare, how they compare to the proposal one. Some comparative points are given. The first one being the performance objectives, which is basically primary quantity that each design method targets, limits, or bases itself upon. The first, some of the methods employ intensity-based approach, while the others, primarily the risk-targeted approaches, while keeping the intensity approach, they include targeting the collapse safety of the structure. Additionally, the proposed framework, together with similar methods, tries to incorporate losses during design as well. The next point is regards seismic hazard, and as you can see, most of the methods utilize uniform hazard spectrum, while others use hazard tied to specific intensity measure. To what regards nonlinearity on how ductile structural behavior is accounted for in different methods, some of the traditional and risk-targeted approaches use behavior factors or viscous damping, while other conceptual and risk-targeted approaches use very extensive nonlinear time history analysis, together with some assumptions regarding the backbone shape of a structure. The frequency spectrum method and the proposed framework use what is called SPO2-IDA tool to derive a dynamic behavior of the structure before running any type of analysis. To what regards relative difficulty and directness, methods that are quite direct are considered as easy, while the others, that is the some conceptual methods and risk-targeted methods, are considered as very extensive or extensive due to the use of some iterations and involvement of nonlinear time history analysis during the design and identification of design solutions. In contrast, the proposed framework and the frequency spectrum method do not use nonlinear time history analysis, but there can be some iterations involved. With regards to flexibility, again, this is based on some subjective opinion. Here, behavior factors are in some methods. Some methods are considered as limited, as there is nothing left to the designer to do, while the others are flexible, as the designer can tailor their design targets beyond what it has been developed for so far. Lastly, the methods are categorized as PBE compliant or not, and as you can see, the traditional methods, some of the traditional and risk-targeted methods are considered non-risk consistent, while the others are. Having seen all the different design approaches, now let's have a look at loss assessment frameworks. In particular, the component-based approach was used within the thesis, which is basically a rigorous methodology requiring full building inventory, along with fragility and consequence functions for each damageable component. Here, decision variables are the deaths, dollars, and downtime, and the toolbox termed as FACT was developed for ease of its application and assessment of losses. And due to its complexity, it is still considered quite discouraging for practitioners to apply. An alternative approach is the use of story loss functions. Here, the assessment is carried out on a story level rather than component level. Also, those are easier to generalize before starting the design, depending on the structure's functionality or typology. With good understanding of current design methods, a framework is proposed for risk-targeted and loss-driven seismic design. As we already saw, traditional methods are easy to implement, but they are not risk-consistent, while in contrast, the PPE-compliant methods are complete and extensive, while complex to implement. Therefore, we decided to propose a framework that is both suitable for both academics and practitioners and traverses the constraints of both types of methods and makes use of the advantages of both to make it applicable. So this is the framework architecture. The steps are detailed, and before embarking on further details, it is important to visualize the framework as a whole with some general sense. While preliminary building information is required in pretty much any methodology, here we also need information on site hazard and performance objectives need to be defined. Additionally, the framework is applied on a story basis. Therefore, story loss functions need to be defined for loss calculations. First, we define the loss curve. Here, parameters regarding different limit states are computed, and based off which engineering demands are computed and refined. Then next stage involves the design spectrum definition, and design engineering parameters are transformed to spectral coordinates for the purpose of computing a feasible period range for the building. Here we ensure that the losses will not be exceeded by the final structural configuration. Next, a backbone curve is established for the desired structure, and SPO2ID is used for computation of mean annual frequency of collapse and computation of a design-based shear force. Step 5 could be considered as quite traditional, as based on the design-based shear, we carry out detailing of the structure. However, if one wishes, the static Kushner analysis may be applied for further refinement of results, or as you may say, for more precise results. Finally, if all performance objectives are satisfactory and detailing requirements have been met, we can consider the design complete. And this is the graphical illustration of the flowchart of the framework. In the first phase of the proposed framework, we identify a suitable loss curve, which is identified through expected loss ratio and mean annual frequency of exceedance. Several limit states might be considered, however, only 3 are considered within this thesis. Those are the operational limit state, where we essentially define initiation of damage and loss, serviceability limit state, where losses are controlled, and collapse limit state, where complete collapse is expected. The design expected annual loss is basically the area under the loss curve. Additionally, the SLS parameters are calibrated so that the EAL is not exceeded, is not exceeding the input of the designer, and those parameters are later used for the computation of the design spectrum and engineering demand parameters. With engineering demand parameters computed before establishing the feasible period range, some refinements can be carried out for more precise results and a definition of a loss curve. By doing so, we can identify the feasible period range. This is where the structure's initial second to yield period must lie. Essentially, we are ensuring that by giving period limits, we are ensuring that the losses associated with observation sensitive components will not be exceeded due to the structure being too stiff, and the structure is not supposed to be too flexible, so that the losses due to displacement sensitive components will not be excessive. By controlling for losses, now it's time to control for collapse safety of the structure. Here, again, several assumptions have to be made regarding lateral strengths of the building and ductility. However, this is an iterative stage for essentially the lateral strength is together with SPO2IDA, we estimate the collapse capacity of the structure, and essentially the lateral strength is computed as a function of this. By using the collapse capacity function and integrating with the hazard curve, we can compute the mean annual frequency of collapse, and this process can be within the framework may be applied multiple times, resulting in identification of a design solution space. Essentially, all design solutions within this range are ensured and satisfying the and following the procedures for the computation of mean annual frequency of collapse. are valid design solutions. Finally, based on this and using the lateral strengths of the building, we can use design codes for detailing of the structural elements. In essence, serviceability limit state design leads to control of expected annual loss, while optimization of mean annual frequency of collapse by nodes through the use of static pushover analysis or SPO2 IDA leads to satisfying collapse safety and performance of objective. So within the thesis in particular, but also to aid seismic design and assessment in general, an SLF estimation framework was developed. The framework consists of building characterization, component inventory sampling, grouping, consideration of possible correlations among the components, application of Monte Carlo simulations for damage state sampling, based on which repair costs are computed, and finally, by using, for example, the medians of the repair cost, a story loss function may be computed through regression. Now let's have a detailed look at the steps. The first step involves the building inventory characterization. Here, the designer needs information on structure's height, global dimensions, occupancy type, and usage. Next, the inventory is identified where component types are defined, quantities, as well as the demand parameters or other necessary metrics. Then, once all inventory is created, depending on the component's engineering demand parameter sensitivity, typology, they can be grouped into different performance groups. Only 3 have been considered within the study. However, more can be added with ease due to its modularity. Those are the peak story drift sensitive structural components, PSD sensitive non-structural components, and peak floor acceleration sensitive non-structural components. Possible correlations of damage states may be considered for structural and non-structural components of the same performance group, given some correlation matrix. The figures demonstrate an associative example of 2 components whose fragility functions are correlated. For example, a causation component, let's say it has been assigned a damage state 3 through simulation, and the dependent component was assigned a damage state 1. In this case, we have a situation that the damage state of dependent component will be pushed to 2, resulting in larger repair costs. Next, Monte Carlo simulations are applied for the sampling of damage states based on which repair costs are computed. This is carried out at each simulation step and for all components using consequence functions. So basically using the quantity of the component and based on the distribution of the cost, a random volume is sampled from the distribution for a specific simulation and assigned to a component. By doing so, for all components, we get the repair cost distributions. Then by using the median values of the distributions, for example, we can select a regression model and compute the story loss functions. This is the example application of the framework. Here we have some story loss functions, as well as the graphical user interface of the framework, along with some the architectural modules. And this is done in Python and is freely available on GitHub. With the method established, it is important to realize how it fares with respect to a more detailed component-based approach. For that purpose, a school building in Italy was used. PACT was used for conducting component-based loss assessment, and more analysis details are available to the reader on the left. The figure on the right is not exactly representative of the school building, obviously, but it's more like a generic representation of how different components, depending on their typology and location, are subdivided into different performance groups. What regards the results, here we have the vulnerability curves and the expected annual loss disaggregation results. And as you can see, the results are matching quite well, with a significant portion coming from non-structural components. Similarly, the following figures provide the relative contributions to the vulnerability curves as a function of return period. As observed, the main contributors at frequent events are the non-structural components, with structural repair costs coming as second. While with higher return periods, we have demolition and collapse cost contributions getting larger as expected. From the figures, again, we have quite good matching between two of the approaches, which is important, as it signifies that the SLF-based approach could be applied without losing the quality of the loss assessment. With the development of story loss functions, it is equally important, if not more, to validate the proposed framework towards its performance objectives. For that purpose, a number of reinforced concrete buildings were used with a space configuration for placement of moment-resisting frames. Residential occupancy was assumed, and components sensitive to peak story drift and peak floor acceleration were used only. Additionally, two site locations were utilized, pertaining to medium and high seismicity regions. To what regards numerical modeling, nonlinear models were created using OpenSys. Here we have some graphical illustrations representing the models, and here in specific, nonlinear element behavior was considered through concentrated plasticity approach, and incremental dynamic analysis was carried out with the purpose of capturing collapse. Again, consistent results were obtained in each case associated with the framework. As you can see, there is very relatively narrow tolerance with respect to the limits and without any case of excessive over-design. This demonstrates the proposed framework's efficiency in obtaining risk-consistent design solutions. Similarly, some risk-targeted approaches showed quite good results, while the cases pertaining to Eurocode show quite a lot of scatter, which is due to the fact that the designs are not risk consistent. However, it is important to note that the values obtained are quite close to the ones available in the literature in Italy and also in the US. Similarly, expected annual losses were validated. As one may see from the results, the EAL values are satisfactory. Consistent results were again obtained in terms of this performance metric, and for some cases, however, the results are not quite close to the limit, which is primarily for medium seismicity region, which could be attributed to the fact that the hazard is not strong enough to result in high losses. It could be argued also that Eurocode cases demonstrate very good results, even closer to the limit. However, it is important to note that the targets for the method for the proposed framework were defined based on the past values of past studies. With that in mind, further analysis of assumptions and design parameters were compared to the actual values obtained. As seen from the figure, flexible buildings have a larger expected annual loss, which could be attributed to the fact that there is high proportional cost of drift-sensitive components. Also, actual loss contributions do not quite match the design values. This is because the design process is such that it is looking for a compromise and assumes singular values for drift and acceleration-sensitive components based on the period limits, while in reality, the cost will vary depending on the structure's initial second-to-yield period. Trying to remedy the extent of the assumption, we had a look at the EDP profiles. A decision was made to use the PSD and PFA profiles obtained after design as benchmarks to scale design EDPs and reapply the proposed framework. By doing so, the expected annual loss limit was reduced from 0.8 to 0.6%, and meaning that the buildings with higher period than the upper limit are no longer satisfying the design, satisfying the performance objective, while the ones within the period limits are quite optimized and closer to the limit. This is entirely an optional step, and to ease its application for the framework, a Python-based framework again was developed to perform the optimizations within seconds or minutes, avoiding extra analysis. To summarize, the focus of the thesis was the development of a framework for design of RC buildings following the risk targeting and loss-driven approach. The goal was to make the complex probabilistic approaches affordable for both academics and practitioners. We aim to fill the gap of lack of practical and customizable tools for easy implementation of STOREY loss functions. The framework is capable of accounting component damage state correlations as well. It was some functions were developed for buildings in Italy and compared to a component-based approach, indicating good matching. Close matching was also observed in terms of loss contributors from different performance groups and per intensity and engineering demand parameter. Additionally, it is important to note that these pre-generated SLFs could act as an important tool, especially for new designs before starting the design and generalizing for a portfolio of buildings of same typologies. Integrated performance seismic design framework was developed and proposed. It was verified and validated through its application towards case study reinforced concrete buildings. Consistent results were obtained in terms of both performance metrics, with targets being met with relatively narrow conservatives and without excessive over-design or multiple design iterations. Methods following other risk-targeted approaches also demonstrated good results, while as expected, Eurocode showed no uniformity in safety across different solutions. It is important to note that the strength of the framework comes from its flexibility and ability to combine the advantages of different methods available in the literature. Also, it was also validated towards expected annual loss, and some further deep dive was carried out into the assumptions involved. It was validated through the application to 3D buildings using bidirectional nonlinear analysis, and it was shown through refinement of EDP profiles that more optimized results may be obtained. Again, a Python-based object-oriented environment was created for ease of its application. Some limitations and further developments could include the possible inclusion of considerations of interactions between components physically located at different stories of the building or pertaining to different performance groups. Also, some parametric and sensitivity studies could further be applied to understand the impact of modeling uncertainties, choice of damping models, and strength stiffness uncertainties of torsional response. It could be also further extended to consider different structural typologies, for example, reinforced concrete walls, steel structures, isolated system within the proposed framework. Okay, thank you.
Thank you, Davit. You saved us 2 minutes. Well done. Okay, so we'll open the discussion.